Okay, so real quick, I gave you this here. Okay, how many sign changes do you guys see up here? Yeah, there's 1, 2. So how many possible positive real roots could it have?
2 or 0.
2, or if there's something that's not real, there's got to be 2 complex. Yeah, positive real roots. Okay, what do I have to do to investigate the negative roots? Put a negative x in. So, what I really want you to understand this shortcut. All the even powers will stay the same sign because when I square a negative, it's positive. So there's no negative to cancel anything or whatever. All the negative terms will change sign. So this stays the same. This changes sign. And real quick, if I take negative 2x cubed and I put a negative x in it, negative cubed is negative times negative is positive. So every odd power will do that. So this stays the same sign. This changes sign. 4 just stays 4. Doesn't care what happens to x. Now how many sign changes do I see? 1, 2. So you gotta scan the whole as you go through. How many times does it change from one term to the next? Twice. So how many negative real roots could there be? 2 or 0. Negative real roots. Okay, maybe. So that's Descartes' rule. In general, it doesn't do much for us, but when it does something for us, it's huge. It'll cut that list in half. That kicks ass. Remember making that list? Remember how long that list gets sometimes? I really want to eliminate some things. What's another way to kind of eliminate some stuff off that list? What's another idea we looked at? Upper bounds and lower bounds. Kick ass. Okay. Anything else about Descartes' rule? Okay. I'm really curious now. I just made this up out of nowhere, but let's see what happens here. I'm going to erase this. You guys ready? Okay. Can you guys tell me the list of possible rational zeros? How do you construct that? What do you do?
Plus or minus all factors of 4.
All the factors of 4. Over?
All the factors.
All the factors of 4. Okay. So you got to make every single combination you can, right? So I could put 1, 2, 4 over 1, so that's 1, 2, 4. And then I can get 1/2, right? Or 1/4. And then 2 halves I have already, because that's 1. 2 fourths I have already. 4 halves I have already, that's 2. 4 fourths is 1. You guys see that? You don't have to list them more than once. You already got those. So let me see if you guys remember, what do you think I would choose to start with to try to synthetically divide by? Keeping in mind the idea of bounds. 4 wouldn't be helpful because it's the extreme, yes? So if it went in and had no sign changes, that would be nothing above 4 is possible. Well, nothing above 4 is possible, right? So maybe 1 or 2. Just let's try 2. I don't know what's going to happen here because I just made this up out of nowhere, but let's see. All right, let's see what happens. Let's see. It's a good review. This is good because the quiz is going to have some of this stuff on it. How do I get this started? Bring down the 4. Multiply 2 by 4 is 8. Add, multiply, add, multiply, add, Come on, I think I did that right. Two things that answer tells you. What's one thing that answer tells you?
It's not 2.
It's not 2. I love it, right? X minus 2 is not a factor.
No positive.
So again,
No positive.
all positive, so that means 2 is in upper bound. So my list, I can now make it 1, 1/2, 1/4, -1, -2, -4, -1/2, -1/4. So I can cancel 2 and 4. All right, you guys. So you got Descartes' rule of signs, which when it works is awesome, but it rarely works. I don't mean it rarely means what it's supposed to mean. I just mean it rarely does something for us, right? If it said 0 negative roots, that's awesome. I can cut my list in half immediately. That's what I mean by works. That's what I mean by works. It gives us something that we can use immediately. Very often it doesn't really do that for us, right? And then you have bounds. Go ahead and synthetically divide that by -2. Let's see what happens. So let me catch up to you guys here. Multiply, add, multiply, add. So you guys got? Okay. What about this? What does this tell you? Yeah, the signs all changed. You see how it's kind of related to Descartes? And it's actually related for the same reason that Descartes kind of works. This is much more useful though. Since I divided by a negative and the signs constantly change, nothing below -2 will work. So now I can eliminate -2 didn't work and -4 doesn't work because it's below -2. Right? Do you guys, so remember this? This is kind of like how this works. What really sucks about factoring things using synthetic division is you just got to get kind of lucky. So what I try to do in a test or a quiz or something is I'll try to make you, I'll say divide synthetically by 4 and -4. What do your results mean? And there'll be bounds, and they'll cut a lot of shit off your list. And then I'll say, what does Descartes' rule of signs say? And it says, there's no negative roots. And so it cuts out all the negatives. You with me? So then you're left with just a few things, so you don't have to rely on luck. Are you guys understanding what I mean by luck? Get this big ass list, any of them could work. So somebody next to you could be lucky and just pick one. You're like picking all the ones that don't work. Oh my God. Right? And time's almost up. That would be evil. So as long as you understand bounds in Descartes' rule, I will help you cut your list down. Yes? Okay. At least I try. Okay. Anything else from homework or just generally, especially considering everybody saw these things? Quiz tomorrow. I'm going to move the test. Test was supposed to be tomorrow, originally. So obviously we're pushing that bad boy back. I'm working on updating the homework sheet, right, with the dates updated and all that kind of stuff. So I'll get that to you as soon as I am done updating it. Yes?
Did you do a 6.1?
Sure. What are we looking at?
What was it? The first one. Number 18.
Oh, yeah.
Kind of showed me yesterday, I didn't really grasp it.
Say again?
You showed me yesterday, but I didn't really grasp it.
All right. Let me see. Alright. I'll do one like it. Okay, so let's look at number 19. 19 says, find the exponential function that passes through 0 to 1,000 and 220, right? Can somebody tell me what an exponential function looks like in general? No, I'm sorry, not the graph, but yeah, what the function looks like.
A to the x.
Yeah, so a, b to the x. So there's two things I don't know, the coefficient and the base. And real quick, I think I said this before, but if I see 2 times 3 to the x, is that 6 to the x? Hell no. All right, so obviously you're going to make a lot of mistakes if you think this is true. How many 2's are here? How many 3's are here? X of them. So let me see if anybody gets this. I could do this. I don't want to do this. All right, what if I had 2 times 3 to the 5th? I can't make 5 6's, correct? Yes? Because how many 2's do I have? Just one. How many 3's do I have? I have 5, yes? But couldn't I take one of the 3's and make it, I can make 1 6, because I have 1 2. Does that make sense? So be careful, you cannot multiply these. You have to do exponents first. So don't multiply those numbers. Okay, I like it. What would this be though? How many 2's do you have?
1.
X of them. How many 3's do you have? X of them. So how many 6's can you make? You can do it, you can do it. I have X2's and I have X3's. How many 6's can you make? X of them. Now you can do it because you have this many 2's and this many 3's. So of course you get this many 6's. Okay, maybe. I might have gone too far. I'm so sorry. In general, you definitely cannot multiply these numbers because they're not to the same power. They don't have the same amount of each. Okay. So, this is what a general, just like we know, can somebody remind me, what's a general form for a parabola, for a quadratic? What's the standard form? I'll get it started. A, x minus h, plus k, k-cats, right? The same way you have to be able to tell me this, you have to be able to tell me this. This is every single exponential function looks like this. Every single parabola, every single quadratic can be put into this form. Okay. So, how does that help me with this shit? Well, what does this tell me? What is 0? What is 2,000? When x is 0, the output is 2,000, right? So then what can I do with that information? So the first piece of information, the output is 2,000 when the input is 0. I just put the information directly in, right? When the input is 0, I get 2,000 output. So what does that do for me? What is b to the 0 power? Freaking 1. Why does that kick ass? Because now I know a is 2,000. I just know a is 2,000 now. You guys get that? That's beautiful. So when they give me points, they give me crazy amounts of information. They tell me, I don't even know what the function is, but I know when I put a 0 into it, I get a 2,000 out. What else do I know? I know this, right? Let me update what's my function look like now, updated with what I know. It looks like f of x equals 2,000 times b to the x, right? So now let's use the other piece of information. When the input is 2, the output is 20. Can you solve that? Can you solve it? Right, what do you do to solve it? What do you do? Say again? Yeah, divide by 2,000. I get 1 over 100 equals b squared, so then what's b? Yeah, it could be 1/10 or negative 1/10, right? So plus or minus 1/10. So then you get, let's see, so we get either this is 2,000 times, and I don't think they tell us, no, okay, times 1/10 to the x, or it's 2,000 times negative 1/10 to the x. And what we normally say is we want the base to be positive, or else it's going to be, if the base is negative, how do I say this? If the base is a negative power, all right, let's look at this for a second. So I'm going to take it to be positive. Real quick, I don't remember if the book says much about this. I really want this to make sense. If the base is negative, what do I get when I put a 0 in there? Still 1, right? Beautiful. I didn't use 0 powers 1. What do I get when I put a 1 in there? Negative 2. What do I get when I put a 2 in there? Positive 4. 3. Negative 8. 4. Holy shit, it's like bum, bam, 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 right? In fact, what do I get when I put a 1/2 in there? What does a 1/2 power mean again? 1/2 power means what? Square root. And what are we trying to not let happen here? I don't want to try to graph using complex numbers, so I don't want a complex number. What's the square root of negative 2? What's the square root of negative 2? Is it real or complex? Complex, right? It would actually be rad 2 I. So the base, we normally have to take it as positive because we don't want to let this kind of thing happen where it just bounces around and it has spots where it's not even real. Okay. Does that help? I mean, so each one of those problems, you just use each point as information. And you slowly kind of determine what A is, and then you get what B is. Yes?
In the book, it shows us how to do on the calculator, how to find it.
How to find what?
I have it on here, I think the other day.
The book shows you how to do this problem on the calculator?
Yeah.
What page? What?
You just go up and it'll just say, you go like, you hit stat.
Oh, I see. All right. We're not going to do that shit. Yeah, so if you know that, you know how to check yourself. On a test or a quiz or something, you're going to have to show me the work.
Right.
I like it. And again, sometimes I have students who are very adamant about, I should be able to use this calculator. Either like my past teacher or this is mine, I should be able to use it. I'm like, I'm not grading your calculator. I'm grading you, right? So most of the time, you can use your calculator to check your work. There are a couple problems like finding the maximum of something that's not a parabola. I'm going to let you use your calculator. I want to test, do you know how to use it? But if I don't say use your calculator, assume I need to see all work, right? Okay, I like it. All right, anything else from homework stuff? Okay. I'm going to ask a question of myself. I'm going to say, Jeff, can we do some more examples of those freaky ass asymptotic functions? And I'll say, sure we can. Let's do these here. Sure. Okay, let's take a look here. Ooh, yeah. That's about as clear as your lecture, Jeff. Okay, let's see. All right, so this quiz tomorrow will have problems like these on it. So, take a minute. I'm going to kind of give you like a minute or two to do each section. So if you want to get ahead, feel free. But go ahead and see if you can find the intercepts. I will tell you this, something weird happens with the y-intercept. So if you're trying to find the y-intercept, what are you guys discovering?
It's simplifying.
Yeah, when you try to make x 0, you get 4 over 0. So there is no y-intercept. And we'll see why in a minute. Okay, so go ahead and find the x-intercepts. Holy crap. All right, so what do you have to look at to get the x-intercepts? So does it make sense? The x-intercepts happen when the whole thing is 0, right? The only way a fraction can be 0 is if the top is 0. And how do you figure out when the top is 0? What do you do with the top? Factor it. So what do you get when you factor this? Yeah, x plus 2 times x plus 2. Okay. We're going to factor the bottom here in a minute. But, so what are the x-intercepts then? Or how many x-intercepts are there? 1. What is it? -2. And what's the multiplicity there? So what's it do there? Turns. Okay, so that's good to know, right? That still holds. The multiplicity idea still works no matter where, if it's multiplying or if it's dividing. Okay. So I give you a little hint here. Don't think I'm going to give you the same hint on the quiz. But vertical asymptotes come from the x values that aren't in the domain. I've got to put a wall there because you're not allowed to go there. So that's where vertical asymptotes are just walls where I'm not allowed to go. So how do I figure out which x values I'm not allowed to use? What can't happen in this problem? What can't happen? This is a division problem, right? Can't divide by, say again?
The denominator can't be 0.
So if I factor the bottom, If I factor the bottom, I can see all the things that I can't use, right? Does anyone see how to factor this? Yeah, take out an x. It's a good first step. And then I'm left with x squared plus 2x minus 8. And how do you factor x squared plus 2x minus 8? X, say again? Plus 4, yeah. X minus 2. Sorry. Thought you said 1. So the vertical asymptotes are the vertical lines through the things that aren't in my domain. I really wanted to make sense. We're not allowed to go there. Just put a freaking wall there, right? So what are those values? What makes the bottom 0? -4. I think I heard somebody say 2. And 0. Yeah, don't forget about the, well, x do. What makes x 0? 0. Oh, okay. So there are 3 vertical asymptotes here, right? Now, so that's where I'm going to put my vertical lines, my vertical dotted lines. And then we're going to run up against that somehow, right? Okay, so part C, I sort of summarized more in English what was on the other sheet about the horizontal asymptotes. So if you forgot how to look at it, read through that, try to figure out what the horizontal asymptote is. I will tell you there's just one. There could be more than one, but it's just one here. So what situation am I in? What's the degree of the top? Second degree? What's the degree of the bottom? Third degree. So I'm in a situation where the top is smaller than the bottom degree. So the bottom is growing much faster. So if I'm dividing by bigger, 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 my outputs are going to go to what? They're going to go to 0. So I'm in this first situation. The degree down below is larger than the degree on top, right? Okay, I like it. Please let that make all the sense in the world. If I'm dividing by something that's just growing really, really fast, my answers are getting really, really small. Maybe. So I gave myself a lot of room here, so I'm going to y equals 0. Okay, there. So let's see what we got. Let's see what we can do. I know my x-intercept. Well, you go ahead and try to put as much down as you can. There we go. Be careful. The last thing you should figure out, one of the last things is, let me say this too. Was it this one or the other one? It's this one. All right, this one is freaky. I would tell you, see here where I say find at most 2 points? For this problem, I would say 4. You're going to need many, many points. So if I gave you this problem, I would say find at most 4 points. then my horizontal axis, what is y equals 0, so that's here. Let's see those. I should be doing this darker pattern. Sorry. That's a little better. Okay. What's it doing at -2 again? What's the function going to do there? What did we figure out? It turns. So do you guys understand? All right, real quick. How many regions have we broken this up into? 1, 2, 3, 4, right? What could it do here, for example, and above that wall? What could it do? It could either be like down here, bless you, right? It could be down here, or it could be up there. Because it's got to slam up against this wall, and then it's got to slam up against that wall. Do you guys see that? So how do I determine which? Yeah, what would you plug in? 3. If you plug 3 in, you get a positive, that's up there. If you get a negative, it's down there. It's that nice. Once you set up your walls to kind of guide your functions, all you need is like maybe a point, and then you know exactly where that thing is going. So let's plug a 3 in. When you plug a 3 in? Nothing too nice, but you know. So when you plug a 3 in on top, you get 3 plus 2, 5 squared is 25. On the bottom, you get 3 times 7 is 21 times 3 minus 2 is 1. So 3 times 7 times 1, I get 25 over 21. Is that cool? Is that all right? Okay. So now watch. I'm not going to plot any points because I haven't determined my y scale yet, right? But I know it's going to be up here, correct? I know it's going to be like this. So let's figure out some more stuff. In here, what's the most obvious point to use? 1. And real quick, is it possible for it to look like a cubic through here? Is it possible for it to do like this or do like this? What would it have to do to be able to go from here up to there? It has to be able to go through the x-axis, right? What's the only place it could go through the x-axis? Here. So if I put 1 into the function and it's here, then it's up here like a parabola. Because it can't, do you guys see, is there a door here? Nope. So it can't go through. So what do I get when I put a 1 in? Let's see. 1 plus 2 is 3 squared is 9. 1 times 5 times -1 is -5. So I get -9/5. Is that what I got before? Yeah, look at me go. -9/5, right? Let's see, this is like 1.05 roughly. And this is, really, Jeff, you could do this. -1.8. Okay. Let's keep going. I'm not ready to make a y scale yet, because I might get a region where the output's 27 or something, right? So what about this region? Do we need any help in here? Why not? I still need help though, right? What's it going to do at -2? It's going to turn. It could either do this or it could do this, yes? So I just need to do 1 point in there. What input do you guys want to use? Well, if I put -2, I get 0. I already know that. -1. Okay, so what do you get when you put a -1 in? I'll cut to the chase. I believe you get 1/9. Is that true? Negative 1 times 3 times negative 3. Yes. Yes, okay. You can double check me on that. So that's really tiny. And then finally back here, isn't it the same situation as up here? It could either be up here or it could be down there. So let's just put a negative 5 in there. Do you guys catch on to what's happening here? It's once I set up those walls, I just need maybe 1 point to tell what side of the walls the function is on. So let's see, I got, what did I get? Negative 9/35, I think, when I did that. Negative 5 plus 2 is, negative 3 squared is 9. And then negative 5 times negative 1 times negative 7 is negative 35, yes. And this is about negative 0.25, I believe. It's almost 9/36, which should be 1/4. Okay, and again, you can just plug it in on calculator. We're gonna plot these by hand, so you don't have to be so precise, but I still want to know kind of like where it is. Sorry, let's now, what kind of scale do you think I should use for the y-axis? I mean, are my outputs very big here? In fact, I would use this. This is where people don't understand. I would use, what would you use, Jeff? 0.25, 0.5, 0.75, 1. Yeah, if we go by 0.25, that'd be nice. See, this is what people don't understand. You have total free reign over what the hell you choose to go by. Negative 0.25, negative 0.5, negative 0.75, negative 1, negative 1.25. All right, let's plot some points. F of negative 5 was negative 0.25. Shlabam. So now this guy is right there. Wee-haw. Right, it's got to slam up against that wall, and it's got to slam up against that wall. F of negative 1 was 1/9, which is 0.1, which is about right there. So this looks like it's got to slam up against that wall. It's got to turn at negative 2 and then slam up against that wall. So it kind of looks parabolic there. It's not really parabolic, but it just looks like it is. F of 1 was negative 1.8, Jeff, you crazy person. Oh, well, too bad. It's way down here. Dang it. It's fine, Jeff. Negative 1.8. So this one's kind of nifty. I should have made a better scale. That's too bad. I didn't look at that close enough. Oh, well. My scale's a little bad. That's okay. So that's way the shit down there. Why do I know it has to turn around like this? Because if it went up, it'd have to go through, and it can't go through. Okay, and then up here, F of 3 was 1.05. So that's way up here. So it looks like, wee-haw, wee. Okay. Crazy sauce. That thing is crazy. Is that what I got before? Yes.
Yay.
Let's check it with Desmos. Actually, yeah, let's do this. How many people would need to borrow a graphing calculator? Anybody? Go ahead and get your graph calculators up, or come up and borrow one if you need one. Oh, that's interesting. Okay. You're good. Need to borrow one, come on up. You're good, at least for the moment. And I gotta recharge these bad boys. You gotta, ready? Let's see, you're good. All right, you got lots of battery. Sweet. Is that everybody? Okay. You guys go ahead and try to graph this on the calculator. Graph that function. let me catch up. Now watch this, you guys. When you're doing this to check your work, you can make the scale the same as what you did on your page. So I'm going to go to Window. I'm going to make X min -5 and X max, oh Jesus. X min -5, there you go, Jeff. And X max 5. I'm going to make Y min -1 point, let's make it -2. Just make sure it fits in there. Up to, what do you got, Jeff? Up to like 1.25, yeah. So I'm going to do that with my window to make it roughly look like what we did on the paper. All right, so here's what we did on the paper. Don't zoom out too much. Okay. And now let's see if I graph this. Dude. So there's this little dude down. See, there's that little dude. There he is. Hey, little dude. And there's this guy up here. And there's this guy, Shonka. And then there's this guy back here. Whee! Okay. You guys got it with me? Is that all right? Now watch. Do you see how this is not quite as like fat as it should be? Right? This one? And let me see what else. Do you see how this is not quite exactly where it should be exactly right? All right, those things are good. Those things are good. It's when I see these looking too much like these, that is a beautiful clue for me that you just copied out of your calculator. So I'd rather your graph not be perfect, because we're doing it by hand. They shouldn't be perfect. Yes? And again, what's the quickest way to lose points on this is to have work that doesn't match with your graph. Right? I mean, that's obviously just copied out of calculator. Okay, so just don't do that. That'll be good. Any questions on that, bless you? Okay, let's do another one. This one, there's one nice thing about this one, but it's going to become bad in a minute. You guys see one nice thing about this one? What's true about the top? It's already factored. That's awesome, right? So what's a really easy intercept to see? Why did I made one with no y-intercept. Go, Jeff. What's the x-intercept? Yeah, x-intercept, -2. Can you guys see that there is no y-intercept? Because what happens when you try to make x 0?
Oh, the bottom.
Bottom is 0, right? I can't have that happen. So there is no y-intercept, no real one anyway. And that's all we're going to graph is real stuff. We don't want to try to graph some 4-dimensional thing. If you do, show me. If anybody graphs a 4-dimensional thing, I want to see it. That'd be really cool. All right, try to do part B. What did I choose to do? Oh, well. Right, for some reason, this is just the GCF down here, right? You just take an X out. But I always get somebody that's trying to do this with this, and that's never going to work. You can't do X, X. I mean, that's not going to work. It's just a GCF. So what are my vertical asymptotes? 0 and 4. Love it. And that explains why there's no y-intercept, because the y-axis is going to be a vertical asymptote. Kick ass.
Why is -2 not an asymptote?
Asymptotes, vertical asymptotes are what makes the function undefined, so we put a wall there. Negative 2 makes the function 0. That's not undefined. Does that make sense? So it's only the bottom 0 that makes the function freak out, and that's why we put a wall there. Right? Okay. Okay. Now, here's the best part of this problem, which you should interpret as the worst part. What situation are we in for horizontal asymptote? What's the degree of the top? Third degree. What's the degree of the bottom? So we're in the situation where the top is higher than the bottom, which means the top is growing faster. So it goes to infinity, but it goes to infinity in a very defined way. So what's the situation I'm in? What does it require? Long division. Oh, yeah. So the really sucky thing about the top being factored for me already is I need to unfactor it. I need to multiply it out so that I can do long division. Some of you guys look appropriately excited by that. All right, I'm going to show you guys a shortcut. This is something you guys should see at some point. Has anyone ever seen this? Have I shown you guys this before? Anybody ever seen this? Does anyone know what it's called? This is called board math. No, this is called Pascal's triangle. Okay, so the way this is created, you start with a 1. You keep putting 1s on the outside. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. Keep putting 1s on the outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Put a 1 on the outside. So on one level, you're like, go math people. Way to play with numbers. But watch this. What is x plus 1 squared? It'll be x squared plus, we write it again here, right? 2x, right? Plus 1. What are the coefficients? 1, 2, 1. If you did it cubed, the coefficients would be 1, 3, 3, 1. If you did it to the 4th power, the coefficient would be, so what's x plus 1 to the 4th? It would be x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Do you understand how much work this would take to do by hand all the way? And how much that shortcut saves me? So, here's the thing you got to be careful about though. So what about x plus 2 cubed? That's what we have, right? Where am I at for x plus 2 cubed? I'm at this level here, right? For the cube. This is the square, this is the first power, and this is a 0 power, right? What's anything to the 0 power? 1. I like it. So, now watch how this works. The coefficients are 1, 3, 3, 1. So it starts off with 1 all x's plus 3, 1 less x, 1 more 2, plus 3, 1 less x, 1 more 2, plus 1, 1 less x, so no x's, 1 more 2, so all 2's. So I get x cubed plus 6x squared plus 12x plus 8. Let's do it the old-fashioned way real quick. Oh boy. Let's do it the old-fashioned way. Let's see if that's what we get. X plus 2, x plus 2, and x plus 2. So this is what I am predicting the answer will be, right? So if I do this, I'm going to get x squared plus 4x plus 4. Is that cool? And then if I do this, I'm going to get x cubed plus 2x squared plus 4x squared plus 8x plus 4x plus 8. So I get x cubed plus 6x squared plus 12. What the shit? Okay, so our little Pascal's triangle is a cool little shortcut. You obviously don't have to use it, but hopefully somebody out there kind of likes it. It's so kick-ass. Anyway, so either way you do it, you get this. Is that cool? So coming back to the problem, I know that this is x cubed plus 6x squared plus 12x plus 8 over x squared minus 4x. Go ahead and long divide that.
Good.
Say what?
That was good.
What do you mean?
What?
I didn't say synthetically divide. I said long divide. You can long divide any damn thing. Yeah, good old long divisions. Well, you're right. That's why you have to long divide, because synthetic won't work. Oh, you can give yourself any room, Jeff. Way to go, buddy. It'll be all right. All right, let me catch up to you guys. X squared times what is x cubed? X times x squared is x cubed. X times negative 4x is negative 4x squared. Change the signs. 20x squared plus 12x. X squared times what is 20x squared? 20. 20x squared minus 80x. Negative plus 92x.
I think it's 16.
I don't know. Where, see? See again?
16.
The 16.
Oh, I see. That's awesome, Jeff. Thank you, thank you. That's a lot better. Okay. So then that's minus 10x squared, and that'll be minus 40, so that's plus 40. Okay, that's better. So these cancel, and you get 52x plus 8. So I get x plus 10 plus 52x plus 8 over x squared minus 4x. Is that what you guys got? Okay, now watch this, now watch. Can somebody tell me again, horizontal asymptotes are all about letting x do what? It's a little bit open-ended of a question, but horizontal asymptotes are all about what the function is doing when x gets really, really... Horizontal asymptotes are all about what the function looks like when x gets really, really, really big, positive or negative. Can you guys see what'll happen if I make x get really big here? Isn't the bottom power bigger? If I let x get really big here, this whole thing goes to 0. Do you guys see that? So when x gets big, this becomes x plus 10 because this part goes to 0. So that'll be the slant asymptote. Now you see why we call it a slant asymptote, because it's a line that's got a slope to it. So it's going to be diagonal asymptote. That's freaky shit. So we got a slant asymptote at x plus 10. So let's see, what can we plot here? I know my x-intercept is -2. I know there's a vertical asymptote at 0 and 4. What am I doing at -2? I should have said this earlier. What's the multiplicity? Third degree. So what am I going to do here? I'm going to go through. Is that cool? Okay. So all I need to know is, okay, so in this region right here, if I'm going to go through this, it's either going to be like this, or it's going to be like this, right? Now it's also got an asymptote. Oh, that's right, x plus 7. So what should I figure out here? What input should I use? What's a good thing to put in to see kind of where this is? -1. So let's see. Right, if I put -1, I can see if it's going like this, or I can see if it's going like that, right? So if I put a -1 in, what do I get? I get 1 over -1 times -5. I get 1/5, it looks like. Oh boy, okay. What about in this region? I got nothing going on in this region here. Let me make this, I gotta use darker thing. So I got this region here. Here. So then I could just pick, I'm gonna just pick 2, that makes sense. Right? It's either gonna be like this, or it's gonna be like this. So f of 2, what's f of 2? It's gonna be, oh boy, it's gonna be 2 plus 2, 4 cubed is 64, divided by 2 is 32, divided by -2 is -16. And again, you just plug in the calculator if you want to. And then finally, I got this region out here, right? So what should I plug in to figure out this region? I should plug 5 in, right? Let's see, 2, 3, 4, 5. If I plug a 5 in, I can see where this thing is. So when I put a 5 in, I'm going to get something insane. 7 cubed. That's 343. Is that right? No. 7 cubed. Is it 343? Oh, good. And then divided by 7 divided by 3. So divided by 21. So I get 343 divided by, no, not 7, Jeff. 5. 5, I just divided by 5, it looks like. Which is 60 something. 68.6. Yeah. Oh my God. Okay. So what kind of scale should I use? I need to be able to go up to 68.6. So maybe I should use a scale of like 20, 40, 60, 80. Or maybe 15, 30, 45, 60, 75. That seems to be all right. Maybe use a scale of 15. You guys see the thought process that goes in? I've got to be able to go up to this. So let me see. If I do 15s. All right, now watch this. I still haven't done my slant asymptote, but now I can. X plus 10. Oh, this is going to be a little bit freaky. But I'm going to do it this way. It starts at 10, yes? Right? That's the y-intercept. And then it goes, and then now let me put a 1 in. When I put a, let's put a 5 in. At 5 it goes up to 15. If I put a -5 in, that goes up to 5. So my slant asymptote looks like that. It's almost horizontal. Okay, so what does this mean? Oh my God, Jeff, what does this mean? So at -1, it was 1/5, which is like right there. So it's doing like this. Oh, this is interesting. Oh yeah, so then it's going to go like that. Whee! It's got to follow this slant asymptote. Oh, this is really funky, Jeff. F of 2 is -16. That's right there, right? -16. So then it's going to have to do like this because it doesn't have any intercepts to go through. And then here, 5 was 68.6. I didn't even plot that yet. 68.6. So here it's going to do like this. That is nice and funky. Nice and funky. It was kind of unfortunate that my slant asymptote was so almost horizontal with my scale, but that's all right. Okay. That is funkadelic. And of course, you can always just check your answer in the graphing calculator. So that's how a slant asymptote works. You graph it just like a normal line, and then it's another wall. Now, do you see how this one goes through it? Why is that okay? Because horizontal asymptotes are what happens when x gets really big. Is x really big here? No, so I can actually go through a horizontal asymptote. I can actually go through it an infinite number of times. I could have a function that looks like, and we will have a function that looks like this. I can have a asymptote, and my function can do this. As long as it's getting closer to it, it doesn't matter if it goes through it. Why is it different from vertical asymptote? Because a vertical asymptote is an x value I cannot use. Horizontal asymptote is just, what does it do as it gets big? It can go, it's fine. Maybe. Oh man, Jeff, that's a lot of shit to throw. All right, I know. They'll be all right. Okay. So you will see problems like this on the quiz. Okay. Let's see. Let's go ahead and check this. Go ahead and put this in the old calculator. Oh wait, not that one, Jeff. This one. If I scale the same. Gonna make my scale the same. -5 to 5 on the x, -75 on the y. Got my function in there. So let's see if I graph this thing. Oh yeah, that's funkadelic. Ooh yeah. So look at that little tiny sliver there. That little tiny, so that's this guy. See, it only has a little bit. So let me make my scale a little bit. Let's go up a little bit more. Let's go up to like 10. See what that looks like. Okay, so there's this piece here. And there's this piece here. Now what you can't see, let me do one little thing. And this is really just because our slant asymptote was so, I'm not sure how to say it, finish that word. -20 up to 30, let's do, just because. There we go. All right, do you see how this is almost making a straight line through here? If I graph x plus 10, I'm going to graph the asymptote. There it is. Do you see how the function is getting closer to that line? Do you see? Okay. Now, in here it looks a little weird because it gets right up against here. So let me do one thing here. I'm going to change my window to be -2 to 2, just to get really close to that, just to see what's going on here. There it goes. See, there's this, and there's that. And of course, that only comes into play when it gets really big. So there's this piece here. And this is this piece, right? In fact, it looks a little bit weird because I'm not really far out enough. So there's this piece here, and there's this piece here. Now look how different this, isn't this a parabola? Sort of, not really a parabola. You can't really see it too well, sorry. You see how this is, do you see right here, it's going down and then over. It's not got the same curvature as a parabola, but on my picture I just made it a parabola because that's all the information I had. That's a good example of I don't want to see this on your graph, because how the hell would you know that from your work? You wouldn't. Maybe. Okay. All right. So, that was a nice little review. Let's do some new stuff, and then we'll call it a day. Just make sure everybody saw these two things, right? Quiz tomorrow, test is moved to the 12th. So tomorrow I'm going to have the practice test. And then Tuesday I'll have the answer key for that, just like before. So that was a nice review of the weirdest parts of 5. The other parts of 5 were the inverse stuff with the radical stuff. And what was 5-7? Was that just Get up there. Oh, yeah, that was inverse and radical. 5-6 is rational functions. 5-5 was zeros. So like the Descartes rule and the bounds and all that kind of stuff. Right? That was 5-5. Okay. So let's do a little review of what we did last time. Can anybody tell me what this is? Yes, what are you thinking to get the answer? So again, true. So you're thinking, what power does 4 need to become 16? It needs a power of 2. Coolness. All right, so that's not too bad. What about this? Log base pi. Log base pi of 1. Base pi. Think about that for a second, right? But this one's an easy answer. I think I heard it. 0, right? Because what's anything to the 0 power? 1. So I don't care what base it is. If there's a 1 there, the answer is 0 because pi to the 0 equals 1. And here, this is true because 4 squared is 16. I like it. See, logarithms, oh God, let them be nice. It's just a matter of internalizing. Do you have an ask? Internalizing what the question is. Okay. Can anybody help me out? Can anybody write that in exponential form? Right now it's in logarithmic form. Can you make that into exponential form? It's basically the same thing we just did here. Right? What must be true? B to the x power is m. That is what this means. Right? Same way I could do this. A cubed equals b. Doesn't that mean that a equals the cube root of b? Yes? Isn't that true? So I can write it in power form or radical form, right? Blah, blah, blah. So here I can write it in logarithmic form or exponential form. So I can go between the two. Okay. Let me see. Do I want, how much time do we have? Maybe we'll do this tomorrow. And I'm going to do, yeah, I like that idea. I have a little like log practice sheet, but I want to do some new stuff. And then we'll do that log practice sheet tomorrow. Okay, so that's some basic stuff. Now this is interesting. And we'll see why this is interesting in a minute. So let's talk about some properties of logarithms. It's log. So one thing is there anything special I can do when it's the log of a product? Yes, there is. I am going to show you something exceptionally freaky. And then I'm going to tell you a nice way to remember the result. So I'm going to prove to you why the result is what it is, and then I'll give you a nice way to remember the result. Okay? So let me do this. I'm gonna kind of show you what this is. It's log base b of m plus log base b of n. So to prove this, right, that's the result. All right, so I kind of said it backwards. To prove this, so if I have log of a product, I can make that the sum of the log of each piece. Okay, that's weird. That is weird. It's very strange. For the proof, just go with me. This is a little weird. Just go with me. Right? I'm going to take these two pieces. Is that cool? I'm just going to take those two pieces, and I want to give them names. What is log base b of m? Does anyone know what that is? You shouldn't, right? So what do we call it when we don't know what it is? X. Okay, so what's log base b of n? Can I call it x? Hell no, because that's what the other dude is. And I don't know if they're equal to each other, right? So what is log base b of n? What can you call it? Y, right? Okay, now stay with me, stay with me. All right, that doesn't, on the surface, it's like, ooh, way to go, Jeff. Good job. What does this mean here? Can you rewrite this in exponential form, these two? What is this in exponential form? We just did this one. B to the x equals m. And what is this in exponential form? B to the y equals n. You guys with me? Okay, so again, so far you're like, way to go, you're rearranging letters. Good job, Jeff. Okay. So you see how there's an m times n here on the other side. So I'm really curious what the hell m times n is. What is m? B to the x. What's n? B to the y. What can I do here? You guys can do this. What can I do in a multiplying like basis? What can I do with powers? X squared times x cubed is x to the fifth. So when I have like bases, what do I do with the powers? What do I do with the powers? Add them. So what is x plus y? Freaking x plus y, Jeff. What the shit? Okay. So this proof, you're not going to have to be able to do this on your own. But I kind of want to see that you see the motivation. I don't know what that is. Let me call it x. I don't know what that is. Let me call it y. Then I can do some shit with it. This side's got m times n. Okay, well that's this. And what does this side want to do to m times n? It wants to take the log. Right? So I get the log of this. Does anyone remember why that's a beautiful thing? Do you guys remember why this is beautiful? Do you see what the answer is to this? Say again?
X plus Y.
Yes, because log base b and b cancel each other, right? Log base b and b to a power are inverses. Or what do you raise b to get b to the x plus y? You raise it to the x plus y. And what is x? It's this, right? And what is y? It's freaking this thing, right? So look what it says. Log base b of m times n equals log base b of n plus log base b of n. Proven. So how is that helpful, Jeff? That's all nice and good and all mathy and shit. How does that help me as a student in your damn class, right? That's what some of you guys are thinking, I'm sure. I know. So here's the practicality of this. Somebody got what you want from this? You don't need anything from this to be honest. But I need to show you this does come from something. We didn't just go, that sounds good. No, it's actually just true. It's just the reality. So, how does this help? Can anyone tell me what log base, what do you got, Jeff? Log base 6 of 2. Does anyone know what that is? No, you shouldn't. Right? I don't know what this shit log. What is 6? What power does 6 need to become 2? That's what it's saying, yes? Do you know what that is? No. I don't know what power 6 needs to become 2. Are you kidding me? I don't know. Okay. So what if I'm going to add to it log base 6 of 3? Does anyone know what log base 6 of 3 is? No, I don't know what I don't know what power 6 needs to become 3. Freaking math, dude. But what does this say if I do this way? How can I rewrite this? Log base 6 of something plus log base 6 of something else equals the log of the product. That's what that says, right? So what can I write this as? Log base 6 of 2 times 3, yes? 2 times 3 is 6. What's log base 6 of 6? Freaking 1. Sweet. I started with shit. Neither one of these I can do. But because of this property, bam! Okay. I'm sorry. I'm excited. This is just cool shit to me. And remember, somebody remember, I don't know if I said this last time, yesterday. What do logarithms represent? Logs are what? I said this a couple times. Why is the log base 6 of 6 equal to 1? Why? Why is that true? Power of 1, right? You're all like, yes, I did say that. It's the power of 1. So logs are freaking powers. That's all they are. Logs are powers. Because when I give you a log question, aren't you saying to yourself, what power does this? That's the answer to a log, is a power. So what do you do with the powers when you multiply two things with like bases? Don't they both have a base b? What do I do with the powers when I multiply two things with like bases? Don't I add the powers? When I multiply two things, I add the powers. Yes? No, I'm trying. So all the properties of logarithms are the same as the properties of powers, because logs are powers. So what do you think this is going to be? What do you do with the powers when you divide two things with the same base? Subtract them. So it'll be the power of the top minus the power of the bottom. That's some crazy shit. Now, does that make sense? Beautiful analogy. Log of a product is addition, log of a division is a difference. That is a nice analogy there. Real quick. Side note. What is log base b of m plus n?
Log base b of m plus.
Nope. It's that. I can't do shit to that. That's what it is. It's just that. I can't do shit to that. I can't do anything to that. That's not what this says, is it? If the inside's a product, I can break it up. If the inside's a division, I can break it up. Here, the inside's a sum. I don't know what that is. What do I do when I add two things with like bases? So, what is b squared plus b cubed? Can you do anything with that? Can't do shit with that. That's what this is saying. When I add two things with like bases, I don't know. I can't do it. But when I multiply two things, then I can add the powers. Do you guys see how it doesn't work both ways, right? Okay, maybe. Now, last thing for today, which is the most important property. I'm going to take property 2 away. Property 2, you're good. We're going to use the shit out of you, but just go away from it. I want to look at property 1. I want to expand on this crazy thing. What do you guys think log base b of m times n times a is?
Log base b of m plus log base b of n.
Log base b of m plus log base b of n. Okay, right? Yay! So just to show you, however many products you have inside the log, you make that many sums, right? So add 3 things in here. 3 things? Sure, 3 things. And then add 3 things over there. Why not? All right, Jeff, that's great. That's nice. That's nice. So, okay, here we go. So, what if I had log base b of m to the p? I know some of you guys are like, God damn, can I get a number up in here? Too bad, we got a bunch of letters. How many m's are in there? And what are they doing to each other? Multiplying, right? Because it's a power. You guys with me? So don't I have log base b of m times m times m times m p times? Yes? That's what m to the p means. P is 7, I got 7 m's multiplying. So p is p, so I got p m's multiplying. Maybe? Can't I do what we just did? Isn't this equal to log base b of m plus log base b of m plus log base b of m plus, and how many of these will I get? P of them. So what's x plus x?
Squared.
What's x plus x?
2x.
2x, okay. What's x plus x plus x? 3x, okay. So what's log base b of m plus log base b of m plus log base b of m p times? P log, so it's plog. I got p of these, don't I? So if I had 2 of them, wouldn't that just be 2 log base b of m? But I have p of them. Now look, here's the shortcut. What happened to this? Didn't it just come down? So don't do all this shit. That's the reason why it works. Now we just can take a power down. And why does it still match with properties of powers? What do I do when I raise something to a power to another power? Right? So if I have b to the x and I raise it to the p, what do I do with the powers? Multiply, right? Are you guys with me? So doesn't that what it's saying? Something, a base to a power is being raised to a power. I multiply the powers. That's what I mean by all the properties of logs are the same as the properties of powers. As I die. So this is going to become crazy important. So real quick, one little example. What was I going to do? I forgot. Oh yeah, log base b of m squared minus log base b of m. There's two different ways to do this. What can I do with this power right there? Bring it down. So what's 2 log base b of m's minus a log base b of m? See again? What's 2 of these minus 1 of these? They get 1 log base b of m, right? Okay, that's one way to do it. One way to do it. Watch this. There's another way to do this. What do you do when you subtract 2 logs, same base? When do you subtract powers when you were doing what? So m squared divided by, what's m squared divided by m? M. Did we get the same answer?
Yeah.
Did it totally two different ways. 2 entirely different ways, we get the same answer. That tells me that we have a nice consistent idea. So everything in mathematics has to be consistent no matter which way you legally attack it. Okay, so let me go ahead and give you this. Be sure to bring this back next time, but we'll do some of this stuff tomorrow. I just want you to have this for now. It's got the properties on one side, and it's got some example problems on the other side. Be sure to bring this back with you. All right. Otherwise, I think that's plenty. I shoved as much into your brains as I could. Go ahead and don't forget